Hello, my name is Richard Lau. In this series of lectures, I'm going to talk to you about the many facets of the petroleum industry. We have designed this series for new engineering students. It may also be beneficial to other professionals who want to increase or update their knowledge. In these lectures, we will start with how the earth was formed, how petroleum was made and accumulated. We'll look at the process of how we decide where to drill for oil, how we actually drill for oil, how we complete oil wells, and how we bring oil to the surface. Then we describe how oil and gas are separated and transported to the refineries. In the refinery section, we will discuss how crude oil is separated into its many products. We will also mention contracts and leasing agreements, health, safety, and environmental items, and marketing issues with respect to getting oil and oil products to customers. Before we look for oil, let's talk about the formation of the earth. Chapter 1, How the Earth was Formed. In this chapter, we're going to talk about the origins of the earth and plate tectonics. To understand where oil and gas come from, we need to understand first how the universe was created and then how the earth was formed from this creation. In discussing the early stages of Earth's creation, we will describe the theory of plate tectonics. In this description, we will see how they move, what happens when they move, and the changes that these movements create. We need to understand plate tectonic theory because it helps us in our quest to locate oil and gas. We'll start at the beginning of the beginning. From physics, we know that the beginning of the universe happened about 13.5 billion years ago. According to them, the universe began with a Big Bang, known as the Big Bang Theory. This theory says that a gigantic explosion produced all the energy and fundamental particles that are in our known universe. That means that everything you see, hear, touch, taste, smell, and know as your physical world was created at that moment. Imagine all of this happening 13.5 billion years ago. Remember, in American English, 1 billion is 1 with 9 zeros. So what was created 13.5 billion years ago? I said all the energy and fundamental particles were created. These particles in physics are called quarks. Quarks make up protons, neutrons, and electrons, which form atoms. Atoms make molecules. Molecules make solids, liquids, and gases, things that make up the earth. The Big Bang created quarks, with some of them turning into hydrogen and helium atoms. Over millions of years, the gravitational attraction between the hydrogen atoms created clouds of gas. These clouds began to spin, contracting to form stars. These collapsing hydrogen atoms started nuclear reactions. These clouds began to spin, contracting to form stars. These stars matured. As they began to die, they exploded into supernovas, gigantic nuclear explosions that created the other 90 or so atoms that we know today. With these new atoms, new clouds again formed by gravitational attraction, creating new solar systems made up of suns and planets throughout the universe. This is how our solar system was first created 4.55 billion years ago. This is how it looks today. This was billions and billions of years ago. It is beyond my understanding. As a human, I really can't understand how long a billion years is. When we speak of millions and billions of years, we refer to time from the point of view of a geologist or a physicist who must use these large numbers to measure the ages of the formation of the Earth, the solar system, or the universe. Of course, in this class, we are interested in the third planet of this solar system, that place we call our planet, planet Earth. Now, let's go back to 4.55 billion years ago. The Earth is a pile of hot stuff. Everywhere there is molten atoms and molecules swirling and starting to coalesce into a round ball of solid matter. There is nothing here that you would recognize as the Earth as you know it. In these early stages, geologists have divided this time into two differentiations, early differentiation and late differentiation. The first 100 million years is called the early differentiation. During this time, two things happened. First, our molten atoms and molecules began to separate, which caused the higher density atoms like iron and nickel to sink toward the center to form the core. Second, the lighter, less dense atoms and molecules formed minerals and other rocks at the surface, which we call the Earth's mantle. In other words, it is during this early differentiation that heavier atoms sink to the core and lighter atoms stay near the surface. In the late differentiation period, we begin to have the formation of gases. The Earth is still very hot, and some of these light atoms that migrated near the surface to form the mantle begin to melt, which creates the crust and releases gases like oxygen, nitrogen, and water vapor. It is during this late differentiation that we begin to see the formation of our crust, our oceans, and our atmosphere. That we begin to see an Earth with familiar form and structure. Formed during late differentiation, the Earth's structure is as follows. The solid inner core is iron-nickel metal. Zone 2 is the liquid outer core made out of liquid iron-nickel metal. Due to the rotation of the Earth, this core swirls and is magnetic. This is where our magnetic fields, which give rise to our north and south poles, come from. Zone 3 is the rocky mantle, made of magnesium and iron silicate minerals. Deep down, it is hot and under high pressure. The rocks here are not really melted. They are soft, like a hot plastic, and can move. Sometimes they are further divided into hard mantle and soft mantle. Zone 4 is the rocky crust, mainly silicate minerals and cations, which are made up of metals. It is in this zone that we find our valuable, mineable minerals. Our continents are formed from the crust. Zone 5 is the hydrosphere, the ocean waters which covers most of the Earth's crust. Zone 6 is the atmosphere, which is the air. It goes from the surface of the continents and the surface of the ocean waters all the way up to about 100 miles into space. Now let's go back to the mantle and crust, zones 3 and 4. Because these are the area of mineral deposits and exploration, geologists have divided these two zones somewhat differently into what we call the asthenosphere and the lithosphere. Let's look at the differences. Geologists made their divisions based on the material strength of the layers, how they behave, not on their composition like in the other zones. The Earth's outer shell is a strong layer made up of the harder mantle and the crust, about 100 to 200 kilometers thick, and is called the lithosphere. It overlies a weaker layer called the asthenosphere, made up of the softer mantle. As I said, the lithosphere shell is made up of the harder mantle and the crust, which we can further divide into oceanic crust under the ocean or continental crust on the land. The lithosphere shell is not a continuous layer. It is formed from a number of fragments or plates that crisscross the Earth's surface. Its upper part, called Teutonic plates, are strong and move over the weaker, softer asthenosphere. These plates move in various directions, away from, toward and sideways from each other, growing the mountains and digging the trenches. Today, satellite measurements have recorded plate movements from 2 to 10 centimeters per year. The lithosphere is of interest to humanity because this is where the minerals are that we need for our existence. The softer, weaker asthenosphere is a plastic. We use the word plastic here to describe a rock that is not a solid nor a liquid and is under high pressure and temperature. The Earth is dynamic. The Moon is static. What I mean to say here when I say the Earth is dynamic, I mean that it changes. As you know, the Earth is always changing. The plates and continents move. We have weather that can change from day to day, season to season, even from millennium to millennium. The opposite of dynamic is static. The Moon is static. It does not change. There are no continents to move, weather to change, or particles to erode. It doesn't even change from day to night. Except for a meteor hitting it every so often, nothing on the Moon changes. Whereas on the Earth, we have water that is moving. We've got weather that is changing. We have the water cycle where water is changing to vapor to liquid to ice. Wind and current that change and causing weathering and erosion. Even the continents are moving, creating and destroying mountains and forming trenches. The Earth is dynamic because things are always changing. All this movement shapes the Earth as we know it, but what forces are causing these changes? What forces cause the Earth to be dynamic? There are two basic forces that shape the Earth's surface: internal and external heat. Internal heat, which comes from within the Earth, moves the tectonic plates. There are two sources of internal heat. The first internal source is the heat left over from the huge amount of energy released during the formation of the Earth. The second comes from the radioactive decay of minerals present in the Earth. The unstable elements are called isotopes. They are atoms, they are unstable, and want to go from an isotope to a stable atom. When this occurs, they give off some gamma rays or particles, which are forms of energy that are released as heat. Where did this radioactive material come from? When the rocks were hot, 4.55 billion years ago, many of these isotopes were formed. Since they can have half-lives of 1 billion years or so, it means that they are still there, and little by little, one at a time, they are slowly going back to their natural state, creating heat, so there's a steady heat coming from the center of the Earth. This is a major source of Earth's internal heat. The external heat, the second source, is solar. The heat we get from the sun. Because of the rotation of the Earth, this heat is not constant, but changes with the seasons and causes climate. We have winter, we have summer. The weather and the climate of the Earth is always changing, creating temperature variations, creating weather. Weather causes weathering and erosion. It controls the water cycle, the wind cycle, the ocean currents. It also permits life. Without the solar energy, our planets and animals couldn't grow. So without the sun, we wouldn't have much life. We need this external heat. We depend on its seasons, its weathering, its erosions, its cycles to give us life. Weathering and erosion are interesting phenomena that take place on the Earth. Called geologically destructive, weathering breaks down the Earth with wind, water, and ice. And then erosion moves it to another place. From our sources of internal and external heat, the rocks on the dynamic Earth also undergo change. This process is known as the rock cycle. Here's a model with our inner core, which is solid. The outer core is very liquid. Sometimes it gets so hot it heats the mantle and the crust, and it breaks out into volcanic chains, causing volcanoes, bringing some of the hot rock up to the surface, creating new crust. This also transfers a lot of heat to the surrounding asthenosphere, creating a conductive heat current which pushes the plates above them in the lithosphere. In some places, new crust is being made, and in some places, old crust is being destroyed from the moving plates. This is part of the rock cycle. Sometimes new rock is being made, sometimes old rock is being destroyed. So the rocks, over millions of years, are always changing.